Hello, thank you for taking the time to listen to my talk today. My name is Tyler Malloy, and the title of my talk is Modeling Human Information Processing Limitations in Learning Tasks with Reinforcement Learning. The foundation of the model that I'm going to talk about today is the rational inattention model of economic decision making. This model differs from the traditional approach of expected utility maximization. A simple example of utility maximization would be making a decision of whether or not to take a bet involving a coin flip or a die roll based on the cost and the expected outcome. The rational inattention model differs from this traditional approach by balancing the expected utility or reward observed by a decision maker with the cost of information that represents the utility cost of gathering information that is required to make the decision X in the state Y. This is done by taking the traditional expected utility model and regularizing it based on the mutual information between the state and decision, which is a measure of the amount of information required to get from an input to an output. In the model, the cost of information is represented by a lambda parameter which regularizes the mutual information measure to relate it to the expected utility. As the cost of information increases, the model will predict the decision maker with more and more informationally simplistic behavior, even at a high degree of potential lost expected utility. Our work seeks to apply lessons from rational inattention in economic decision making into the domain of modeling differences in human information processing abilities in learning tasks. A popular model of human learning is reinforcement learning, which represents human learning as updating estimates of the values of performing actions in different states of the learning environment. These models represent learned behavior in the form of the policy function, which maps the state of the agent onto a probability distribution over actions they can perform. However, this method doesn't take into account natural limitations in information processing abilities. What we would like is a measure of the cognitive requirements of a decision in a learning environment in terms of information. By relating the rational inattention model into the domain of reinforcement learning, we developed a model that can incorporate this desired feature. The result is a model with a parameter that represents differences in cognitive abilities in an information theoretic sense. The way this is done is by representing the cognitive difficulty of a given policy by its mutual information. While training the model, we ensure that the information being used to represent behavior is below the information processing capacity parameter. The individual information capacity parameter is optimized over the entire dataset of a human participant's decisions in a learning task I will discuss next. The dataset used to predict human decision-making came from a previous study that had participants make selections between 3 different options consisting of 9 total features, each appearing once, with one feature being associated with a higher probability of receiving a reward. After each selection, the 9 features were randomized within the 3 choices, and the participants continued making selections and learning which of the 9 features was associated with a higher probability of a reward. Additionally, this task consisted of 2 different types of responses, one where the participant needed to respond quickly, and another where they had more time. This is an important feature of this learning task for the capacity limited method, since ideally the individual information capacity would be the same in these different tasks. The following results compare the capacity limited method with the best performing method from the original paper describing this dataset. As we can see, there is a modest improvement in predictive accuracy from the capacity limited model. But more importantly, the way that this is done is by representing each human participant's capacity for processing information in these different learning tasks with a single parameter that is kept the same for all trials. This demonstrates that it is possible to build reinforcement learning models that capture some aspect of individual human cognitive abilities while predicting decision-making to a high degree of accuracy. Although the sources of differences in performance are not only the result of cognitive limitations, other things being motivation and attention, all of these factors impact the ultimate information processing capacity of these participants during learning. The implication of this research is a broader understanding of how individual cognitive limitations impact learning.